All right, Math 2, we've got lesson 7.1.1, Explore Conjecture Proof. We're going to do this in 2 days since it's a little bit long. So here's the first half of the lesson. Okay, our goal is to show that we can use congruent triangles to find different properties from quadrilaterals. So we're going to start with a parallelogram. A parallelogram can be made if I take a triangle and then rotate it about the triangle's midpoint. So that would create a parallelogram. First thing we're going to do is we're going to mark the congruent angles on the rotated triangle. So this triangle got rotated. So that means this angle rotated all the way down over to here. So I'm going to put one angle mark over there. These two would have to be the same. This angle would have been rotated all the way back over to here. And those two would have to be the same. And then this angle, if I rotated 180 degrees, over here would be this angle. So I can see these are the same triangle. It's just this one got rotated. And when you rotate a triangle about the midpoint right here, you get a parallelogram. Now, how can we prove that this is definitely a parallelogram? Where a parallelogram has two pairs of parallel sides. So can I show that these two sides are parallel? And the answer is yes. Here's how I can do it. I've got this angle here and this angle here, and they are congruent angles. Now, those angles would also be called alternate interior angles. If alternate interior angles are congruent, then these lines have to be parallel. So since these two that are marked with 3 tick marks, they're alternate interior angles where this would be the diagonal would be the transversal and these two sides would be the parallel lines, those would be alternate interior angles. Going the other way, this angle and this angle are congruent to each other. And those are alternate interior angles, which proves that this side and this side have to be parallel to each other. So because the alternate interior angles are congruent, the sides have to be parallel that are making them. So it's kind of like called the converse of alternate interior angles. So alternate interior angles are congruent. Which proves that the opposite sides are parallel. List the other characteristics of the parallelograms by looking at the congruent triangles. Well, we can find other things that are going to be congruent. For instance, since this side here was rotated all the way to over here, these two sides have to be congruent to each other. And then this side here, this side was rotated all around to this side. So it looks like a new characteristic of a parallelogram is that the opposite sides have to be congruent to each other. Since these two triangles are congruent, these are corresponding parts of congruent triangles. So it looks like that we can say that the opposite sides are congruent to each other. It also looks like the opposite angles are congruent. This is a 2 tick mark angle, and that's a 2 tick mark angle. So those opposite angles are congruent. This angle over here is 1 tick mark plus 3 tick marks. And this angle is 1 tick mark plus 3 tick marks. So that means that those two angles have to be the same. So the opposite angles are congruent. So looking at those congruent parts of those two congruent triangles, we can find out a whole bunch of stuff that we think is going to be true about those triangles. All right, so Next, we're going to use the definition of a parallelogram to prove some of the things that we have just made a conjecture about. Because what we've done here is we've explored by rotating this and saying, okay, if I rotate this triangle and make this shape, what's going to happen? And we made conjectures. It looks like the opposite sides have to be congruent, and it looks like the opposite angles are congruent. Now we're going to prove it using, well, proofs. So here we go. We're going to start with the definition of a parallelogram, and it's simply a quadrilateral, so that means 4 sides, with 2 pairs of parallel lines, or parallel sides. Wow, words are hard. All right, so we're going to use the definition of a parallelogram to prove that a diagonal always splits the quadrilateral into 2 congruent triangles. Now, we said we think that's happening because that's what we did up here. We rotated it, and it looked like those 2 congruent triangles actually made a parallelogram. So now we're going to prove that these 2 are actually congruent triangles. And if they are congruent triangles, then all this stuff that we were working on down here is actually true. All right, so we're going to start off with what we're given. We're given that that's a parallelogram. And by the definition of parallelogram, we know that we have parallel sides. So we're going to start with what we were given. What color? We'll go with this one. So we'll say that quadrilateral ABCD is a parallelogram. All right, that's what we are given to start off with. And let's try to prove that these 2 triangles are congruent to each other. So this is given. Okay, so if it's a parallelogram, 2 things become true. I know that this side is parallel to this side, and I know that this side is parallel to this side. So let's write those 2 statements down. We know that AD is parallel to BC. And we know that AB is parallel to DC. Kind of writing small so I can fit everything because I know this is going to be a big one. All right, the reason for both of these statements is the definition of a parallelogram. We said definition of parallelogram was we have 2 pairs of parallel sides. So we'll just say definition of parallelogram for both of those. All right, let's go to this side. If I know that AD is parallel to BC, then I can say that this angle and this angle are congruent because if they're parallel, then alternate interior angles are congruent. So when we have parallel lines, alternate interior angles are congruent. So now we can say that the angle ADB is congruent to angle CBD. And that's because alternate interior angles are congruent. Technically, we would say when 2 parallel lines cut by a transversal, then the alternate interior angles are congruent, but we're not going to state all that. We're just going to say alternate interior angles are congruent. So we'll just go with that. Okay, over here, AB and DC, that's the top and bottom here, if those are congruent, are parallel to each other, then I have alternate interior angles going this way. And so now I can state, based off of this piece of information, the angle ADB is congruent to angle CBD. Or did I do the wrong angles? Sure did. It's supposed to be BDC. Oh, man. So that's supposed to be BDC. Sorry. So BDC, this one, is congruent to ABD. Wow. All right. Paying attention now, I promise. So this is the same reason. We know that alternate interior angles are congruent. All right, so I want to prove these two triangles are congruent. I have two congruent parts. I have a third congruent part using the reflexive property. I know that BD from one triangle is congruent to BD from the other triangle. So now I can state that BD is congruent to BD. And that's because of the reflexive property. So now I've got an angle, a side, and an angle on both of them. So that proves the two triangles are congruent by ASA. So because I know this, and I know this, and I know this, I can now state that triangle, let's see, let's do DAB. So triangle DAB is congruent to triangle. Let's see, I did D over here, so I have to start with B over here, so BCD. So I just proved that those triangles have to be congruent by angle side angle. So what we're saying here is what we explored over here is actually true. We said it looks like when we rotate about the midpoint that we get a parallelogram. So if I take two congruent triangles and rotate them, it looks like it makes a parallelogram. Well, here we just proved that yes, if you've got a diagonal there, you do have two congruent triangles. So our exploration up there is actually true. Now we're going to extend the proof and show that the opposite sides are congruent. Now notice I have not marked these sides congruent. Instead, I've marked them parallel. So what we can do now is we can say, since the triangles are congruent, all the corresponding parts are congruent in the triangle too. So now I can come off of this statement and say, okay, these two triangles are congruent, so AD and BC are corresponding parts, and AD would be congruent to BC. And you can say it a bunch of different ways. I like just saying CPCTC. Corresponding parts of congruent triangles are congruent. And over here, so we said that AD and BC were congruent because they're corresponding parts of congruent triangles. And then AB is congruent to DC. Also because of corresponding parts of congruent triangles are congruent. There we go. Backside. Oh, that's not the back. Here it is. All right, Kip is confused. Come on, Kip. So Kip's confused. He put his two triangles together, but he doesn't get a parallelogram. So Kip's got this triangle. He tried to put them together, and he's like, oh man, I'm not getting a parallelogram. What did I do wrong? What did he do? Instead of a rotation, Kip reflected. Silly goose. So Kip did a reflection instead of a rotation. Come on, Kip. All right, identify what shape he made. And it says use the math notes. That's the methods and meaning section at the end of this unit. Well, if you look at that methods and meaning sections, one of your shapes is called a kite. And this is indeed a kite. All right, what do congruent triangles tell us about the angles of kites? Good question. Well, it tells us that these two angles are congruent, but these two big angles on this kite aren't necessarily going to be congruent. So it looks like a kite has one pair of congruent angles, these angles over here, because those are corresponding parts. So a kite has one pair of corresponding congruent angles. What do congruent triangles tell us about the diagonals of a kite? That's interesting. Well, let's see if we can figure out what it says about the diagonals of a kite. So this is a diagonal here. If I wanted a second diagonal, I could put a second diagonal here. But just looking at this diagonal here, I skipped ahead, sorry. Skipping ahead, let's go back. So I've already got a diagonal here. These two correspond to each other, so this is going to be congruent to this one. And then it looks like these two sides are going to be congruent because those are corresponding parts. Remember, we got side, side, side right here, or side, 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 because these are just a reflection. So this is reflexive property, that got reflected, and that got reflected. So it looks like a kite has two sets of congruent, that they're adjacent sides that are congruent. So we'll just call that two pairs of adjacent congruent sides. All right, last part for today. We're now going to explore, conjecture, and prove with a kite. Okay, so we've got a kite here. We just showed that a kite has these two sides congruent. We found that out because we reflected over here. We're going to explore what does it mean for the diagonals. I've got one diagonal here, and here's what I was trying to get ahead earlier. Let's see if we can explore and find out anything about our diagonals. So here I've got the diagonal, that's from the reflection, and there's a second diagonal here. So we're exploring the diagonals. Now looking at the diagonals, we might make some conjectures about the relationships that we see between those diagonals. So maybe you look at that and go, oh, you know what? That looks like that's a right angle. So that looks perpendicular right there. So we might say that the diagonals are perpendicular. When we make conjecture, they're educated guesses. We have to prove them later. So it looks like the diagonals are perpendicular. You might also look at it and say, you know what? This diagonal looks like it's cutting this diagonal in half. So it looks like one of these diagonals is bisected. All right, those are our ideas, our thoughts of what's going on here. We drew another diagonal on here just to explore any relationships we might see. We made a conjecture, an educated guess, that it looks like the diagonals of a kite are perpendicular to each other. And it also looks like this diagonal got bisected, meaning that this side's congruent to that side. Now we're going to prove it with a flowchart that those two conjectures are actually true. All right, so we explore, we try something new out, we make conjectures, we make guesses based on what we've seen, and now we're going to prove that this is true. So we made a conjecture up here, a rigid transformation, and we said that the reflection causes a kite. So we're going to start off, we should probably name these two triangles. Let's call this A, B, C, D, yeah, I'll call this E. All right, so let's say that we're going to start off by saying that this triangle ABC is congruent to triangle ADC. Let's say that that's what we're starting off with. This is kind of given to us. It's given because of that reflection that Kip did earlier. All right, since it is congruent, these two triangles are congruent to each other, we can then say that we have a bunch of congruent sides. All right. Oh, just a second, I gotta blow my nose. All right, back. So here's what we're going to do. We're going to start by proving that these are bisected here, that this diagonal is bisected. If they're bisected, then this side's congruent to that side. That's what a bisector means, right? All right, so since I know this triangle is congruent to this triangle, here's some of the things that I can say. First of all, I can say that AB is congruent to AD. Ooh. Because they're corresponding parts of congruent triangles, right? These two triangles are congruent, and those are corresponding parts. So that's CPCTC. The next thing I can say is, since this is a reflection, this angle is the same as this angle. Because remember, we reflected, Kip reflected it. We didn't do it. Kip was the one making the errors. Stupid lights. Oh, I hate you. All right, get back up. Back to work. Okay, so this looks like angle BAE. Is congruent to angle EAD. So we're just looking at these two top triangles here. That's also CPCTC. So because I have this statement, I can make these two statements. Now I can make a third statement that AE is congruent to AE. How do I know that? Because of the reflexive property. So I now know that this triangle here is congruent to this triangle here. We already knew that these big triangles were congruent. Now we've just proven that these two small triangles are congruent. Because what do we have? We've got side, angle, side right there. So by side, angle, side, those two triangles are congruent. So now I can say that triangle, hope I don't run out of room here, triangle BAE is congruent to triangle DAE. Bay is congruent to day. So knowing those three pieces of information, I can say that those two triangles are congruent because I've got side, angle, side congruence. Okay, I just got done saying these two triangles are congruent. So let's go this direction. Because those two triangles are congruent, this triangle is the same as this triangle, BE and ED have to be congruent. Because they're corresponding parts of congruent triangles. And corresponding parts of congruent triangles are congruent, CPCTC. So we just said that this and this, they're congruent to each other by CPCTC. We just got done proving the triangles are congruent, so these two parts have to be congruent to each other. All right. Now, since those two parts are congruent, that means E is the midpoint of BD, because that's the definition of a midpoint. A midpoint splits a segment into two congruent parts. These are two congruent parts. So we can say that E is the midpoint of BD. And that's the definition of a midpoint. And lastly, we can say that this line is bisecting this line because a bisector goes through the midpoint. So this line is going through the midpoint of this line, so that means it's bisecting it. So we were right. One diagonal is bisecting because this line, this diagonal, is bisecting the other one because it's going through the midpoint. So my last statement is that AC bisects the other diagonal. What did we call it? BD. And that's just the definition of a bisector. All right, so we have just proven our conjecture that one of the diagonals is bisected. Now we have to prove that the diagonals are perpendicular to each other. Here's my plan for that. So I know that this is a straight line. I know that these two angles, since we just got done proving these two triangles are congruent, I know that these two angles are the same. If they're the same, and this is a straight line which is 180 degrees, they both have to be 90. Therefore, these two lines are perpendicular to each other. Sounds like a lot. It's not that bad. All right, so here's what we're going to say. We're going to say that this angle here, AEB, is congruent to angle AED. Oops, ED. And that's CPCTC. Their corresponding parts. CPCTC. Okay? I also know that if they are congruent to each other, that means their measurements are equal to each other. So the measurement of angle AEB is equal to the measurement of angle AED. That's the definition of congruence. On top of that, I know that these two angles have to add up to 180 degrees because they're linear pairs, and linear pairs are supplementary. So I'm going to say that the measurement of angle AEB, this one, plus the measurement of angle AED equals 180, because we know that linear pairs are supplementary. No, don't die on me. Please. Okay, it's coming back. I really like this pen. Okay, so linear pairs are supplementary. Now look what we can do. We can say that since these are the same, and since they also add up to 180, that they must both be 90. We can say that the measurement of angle AEB is 90 degrees, and that the measurement of angle AED is 90 degrees because of these two statements. We said they're equal to each other, and they add up to 180. If they're equal and add to 180, they must both be 90. We can just substitute in numbers there. If they're the same and they're equal to each other, they have to be 90. So we'll just call this substitution. I probably would call it something else, but that would take several more steps. So the book calls it substitution. We'll just go with the book. All right. And then finally, since those are both 90, then those have to be right angles, because that's what the definition of perpendicular means. So now the diagonals AC has to be perpendicular to BD, because those two lines make right angles, 90-degree angles. Therefore, definition of perpendicular, they have to be perpendicular lines. Done. All right, yeah, that's just the first part. We still have another big old proof to do. So anyways, this is how rules come about in math. You explore stuff, you try new things out, you make guesses, educated guesses, and then you prove them mathematically whether your guesses were right or not. And that's what we've done. All right, math hard. See you next time.